Hello everyone, welcome back to our blockchains course. We are now looking at different blockchain platforms. This lecture and the next one is we're going to be discussing Corda. This is the first part of Corda. Corda is really a permissioned blockchain network, or I shouldn't really say it's a blockchain because I should call it a distributed ledger. But there isn't a blockchain in Corda. For instance, there isn't a notion of fully ordered transactions that are all hash chained together. So there is no really a blockchain as such. But it is a distributed ledger with consensus. So we'll talk about how that works. And Corda has been designed specifically considering the requirements of financial services use cases. So a bunch of banks have come together to form a consortium called R3. And R3 leads the development of Corda and also the governance around the Corda development itself. Right? It's specifically designed considering data privacy as a first-class requirement. And Corda was open sourced in November 2016 and has been seeing a good amount of progress in terms of capabilities over the last year and a half. R3 is coming out with an enterprise version of Corda, and it's compatible with the open source version with some improvements, right? So they are promising higher availability and performance, enhanced security using Intel SGX and the notion of enclaves for secure execution, and also integration with hardware security modules for key management. They're also bringing in a modular database, so you can use different relational databases along with Corda, and it also brings in integration with LDAP and Active Directory. R3, the consortium of financial institutions, has partnered with Microsoft to offer Corda on Microsoft Azure, on cloud. It's also available on AWS Marketplace. So it's now available for you to instantiate on a public cloud and try it out. So let's look at some of the concepts, right? So I'm going to talk about some of the higher level concepts and then we'll get into some of the details of the technical details itself. So as a foundational concept, R3's founders and Corda's creators, they felt that with financial services use cases, legal agreements are a critical part of those use cases. So this could be agreements between banks on how they are going to operate on assumption of liability and risk. It could be regulatory agreements, maybe between a regulator and a bank. So they want to associate smart contracts with legal agreements. So this is a fundamentally philosophically different notion from Ethereum, like we discussed in the previous lectures. Ethereum, as I mentioned, considered code is the law, right? But in Corda, they consider the code and the legal agreement as two distinct aspects. The code is something that tries to support what is mentioned in the legal agreement, but is distinct from the legal agreement. So the legal agreement is what is going to be acceptable in a court of law, but the code, the smart contract code, and the distributed ledger information can support a legal agreement, but is not really legally admissible. So elements of a legal agreement, so this you can think of it as it's going to be captured as a document. It can be stored together with the smart contract. So that could be, this is optional, but typically there is a legal agreement that goes together with a smart contract, whether it's a bond issuance or anything else, right? That you might see in or a stock market exchange. Any of those, there are legal agreements that are associated with the smart contracts. So the parties of the agreement are specified. The time windows for when the contract is valid, so it's valid before a particular expiry date or until a particular maturity date. Maybe there's an agreement for, let's say, a term deposit, so there's a maturity rate for it, or a duration, a period of time. There could be external facts and conditions that govern the contract. And these facts may be provided by oracles. So oracles are also a first-class entity in Corda. So we'll talk about that in the next lecture, not this one. And these external facts can be various, right? It could be particular interest rates that are fixed. It could be a share price that changes over time, but it's fixed for all users at any given point of time. It could be foreign exchange conversions. There are many different notions of external facts that might influence a contract. And these external facts are provided to the contract through trusted oracles. There could be witnesses. There are terms and conditions of the contract. This could be in legal prose. And there could always be supporting documents and attachments along with the legal agreement. And you can actually track the life cycle of the agreement itself from creation to amendment to actual execution of the agreement to an exit, right, where the agreement is no longer valid. Right, so all of this is then captured as a legal agreement and goes together with a smart contract. So what are some of the key design principles of Corda itself? So the first very fundamental and a very unique principle of Corda is that it does not have any global broadcast. So if you look at any other blockchain platform, there's typically an exchange of information. It could be transactions typically that are spread across the network, and all the network participants will get that transaction information. So there is a global broadcast inherently part of every blockchain platform. Corda, in stark contrast, because they value privacy and they want to build that in as a first-class construct, there is no global broadcast. So all the message exchange are peer-to-peer. So you can only point to another peer and send a message to them. You can't send a message across to the entire network. And that's also fundamental because you don't want to send messages. You want to keep messages private, and only authorized entities should be recipients of that message. No blockchain, as I mentioned. So it's going to be a distributed ledger. So every node will maintain its own ledger. And in some sense, the global distributed ledger is a union of all these ledgers. So we'll see how that, we'll talk about how that works. It does use a UTXO state machine model, and it does have a way to verify that you are actually trying to use unspent transactions and you're not trying to double spend in any way. It's not an account-based model. So Fabric and Ethereum use an account-based model where there are accounts and accounts can store arbitrary state. Whereas here there is a UTXO model, and you're only going to be transacting with unspent transactions. It is a permission network, so it is going to have identity issuance on the network that is trusted, that is issued by a trusted doorman service. We'll briefly talk about that as well. All communication between nodes is direct. As I mentioned, it has to be addressed to a particular recipient. It is encrypted using TLS, so it's secure. So it's a secure message exchange. It's sent over AMQP, right? There are no global broadcasts. The ledger itself is a relational database. So the smart contract can invoke SQL queries to read and write from the database, which is the ledger. We'll talk about details of how the ledger itself is composed. And the smart contract itself is based on any JVM-based language. You can use your contract in any JVM-based language. Typically, it's Kotlin, right? Some of the contracts that they've written are in Kotlin. And the virtual machine, like Ethereum has the Ethereum virtual machine, the contracts run in a JVM-based virtual machine. So it's a Java virtual machine on which these contracts run. So that's some of the key design principles. Corda is, of course, a peer-to-peer network. There are multiple entities of this network. Let's say Alice, Bob, and Charlie. These could be banks, it could be financial institutions, it could be others who are part of this Corda network. There are other entities like notaries and oracles. These are in some ways trusted entities. We'll talk about the function of notaries and oracles in the next lecture. Once we understand how the Corda system, the basic set of transactions and contracts work in Corda. Right? So all the message exchanges between peers as well as notaries and oracles, all of them happen over TLS encrypted messages sent over AMQP. There is, as I mentioned, there's a domain service. The domain service is the one that's going to do some form of KYC, so know your customer. They will make sure these are legitimate entities and they require access into this network. They need to be part of this Corda network. And the doorman, once it's approved this entity for access, it then issues a an identity based on a TLS cert. And this is from a permissioning service. So it then issues this identity, and the permissioning service creates the cert for the participating entities. So this is how the permissioning itself works. So there is a domain service providing KYC, and then the permission service that issues the certificate itself once the domain service enrolls it. There is a network map service that maps entities to their peer IP addresses as well as their identity. So this is how people will know which entities are part of the system. How do I send a message to another peer? What is the IP address on which I should send it? What is their certificate that I should address it by? So all that is captured in a network map service that is maintained by the network, and anyone can query it. So the Corda node itself, as I mentioned, runs on a Java virtual machine. All the state information is stored in an RDBMS. It's a relational database. There's a AMQP messaging service. That's how peer-to-peer message exchanges happen. Then there could be one or more Corda services, and then Corda applications, right, that are running in a single node. Apart from just a private permissioned network, R3 or the Corda community envisions really a network of networks to evolve. So there could be, for instance, a network of entities working on a shared KYC application. There could be another network of entities working on bank guarantees, another network for trade finance, and so on. Right? These could be overlapping networks, so there could be common entities in this network. It's entirely possible. But the Corda R3 really envisions all of these blockchain networks, independent blockchain networks, to actually be interacting with one another. They might be leveraging the same oracles for trusted information. They could be using the same notaries, for instance. There could be overlap in some of these functions. But apart all of these networks are connected in a global interoperability zone. So this global interoperability zone is really that gets you the notion of a public network. So this connection between multiple private networks in a globally shared network gives you both the privacy of permission networks as well as the interoperability across networks. So I want to do something on KYC, and then I want to issue a bank guarantee. So all of these things can be interoperable and part of a globally shared network. It allows, so each node operates within a particular zone, and it can transact with other nodes in that zone. Right? So the global Corda network allows assets to flow across from one zone to another. So asset can be created in one zone, and then it can be transferred over to another zone. So those sorts of interoperability functions will become possible with this global interoperability zone. So Corda 3.0 delivered a stable protocol for this, and the future versions of Corda will be compatible with this. So this really allows multiple networks to be interoperable and assets to be taken from one network to another network, and nodes to really transact across these different zones. Okay, now coming to the transaction model itself, right? So Corda uses a UTXO model. How it works is each time a new transaction is created, it has a reference back to a previous transaction that is unspent. And then once the new transaction is created, the previous transaction is marked as historic. The historic basically is synonymous with being consumed or that transaction being spent. And this provides a full audit trail. So because of these links from one state to another, you can have a full audit trail of all of these agreements over a period of time. So for instance, if you're maintaining balance in some sense, Alice's balance. So you could have a transaction where Alice pays Alice borrows money from Bob, and then Alice may repay a part of that money. So all of these are recorded as independent transactions, and as a new transaction gets added, the previous transaction that it refers to is marked as spent. This is very similar to the UTXO model, except that each of these transactions is going to hold state. The states, unlike Bitcoin, although this is UTXO, unlike Bitcoin, where Bitcoin only refers to Bitcoin input and Bitcoin output, here you can really, in your state information, you can actually have arbitrary data. So this can really refer to maybe a table in your database and have data pertaining to different rows and columns of that table. So arbitrary data can be captured as part of state, but as and when state gets modified, previous states are linked and they are marked as historic. So that way states, once they are historic, they are immutable and represent a shared fact. So as and when states get created, they are all immutable. So again, it's a append only log of transactions, but it's just that it's not a globally synchronized log. So all nodes are not maintaining a single blockchain in some sense. So this is just a pictorial view of how UTXO works. This is inputs and outputs again, but just that inputs and outputs can have arbitrary data. Okay, now coming to the storage aspect itself, right? Each node in the network maintains a vault, right? It's called a vault, and it's really a database that tracks all the data that node is privy to, right? So it has all the current and historic states for that node. And different nodes can actually have different view of state information. So there could be data that's shared between 3 parties, only those 3 will hold it. There could be other data that's held by just 2 of them, only those 2 hold it, the third party does not hold it, and so on. So these vaults are currently based on H2 embedded SQL engine, and they are also planning to support JDBC. I haven't looked recently whether they've actually added that, but I believe they can support any relational database. The current state of the ledger comprises of all the unconsumed transactions. So it's very similar to UTXO. So you can have a sequence of these transactions. The unconsumed state is the current state. Rest of it is historic state. Corda allows for fine-grained access control on the state sequence. So I can say who gets access to which state information. I can do that in a fine-grained manner. Fabric, in contrast, allows this data partitioning through the notion of channels and collections. In Corda, just the way the message passing works and how the transactions are shared, we'll see how that works. That itself gives you a very strong notion of privacy, right? Only the participants of a transaction will ever see the transaction and the data within it. So then how does the distributed ledger work will be the next couple of slides. So the Corda ledger. So let's look at this, right? So let's say Alice is one node and Bob is another node. So there are certain set of shared facts between Alice and Bob. So in this case 1 and 7 are shared facts between Alice and Bob. So both of them will store them on their respective ledgers. So Alice stores 1 and 7. So the facts of them are there. Apart from this, Alice might have some state that is not known to Bob, and it will store it on its ledger. Likewise, Bob has some state that's not known to Alice. So that's 5 and 6. That's stored in Bob's ledger, but not on Alice's. So the vault for each peer is distinct from the other peers, and it has only the data that is private to that node, or that node is aware of. And again, there is no global broadcast. So no node will know the universal or the full superset of all of this information. If you want to look at it as the global state of the network itself, you can think of it as the global state of the network, or all the facts known by the network is really the union of all the facts known by each entity, right? So if you put that all together, that'll be the global knowledge, but no one entity maintains that. So all facts are split on and shared only by the parties private to that fact or that transaction. So it has no notion of accounts. It is only facts and information that's stored amongst parties. Transaction ordering is enforced by hash functions based on previous states. So in some sense, this is not a total ordering. There's only a partial ordering between transactions. So you know that one transaction consumed information from a previous transaction. So there is a link between those two. So there is a dependency and an ordering. But there could be transactions where there is no ordering, right? Or at least at the level of a single peer, they might be parallel transactions. Consensus allows you to identify essentially the double spending problem and determines whether a transaction is valid or not. So we'll discuss consensus. And it all because of the fact that we have a full sequence of the provenance of everything that has happened, auditability is also achieved, right? So you can get a full history of all activity that is recorded on each peer. So this is again a fundamental difference. Fabric, Ethereum, all of those things, they all are based on a Fabric, and all other permissioned networks are based on a broadcast architecture. When I said Ethereum, I meant the permissioned versions of Ethereum. Corda takes a very drastically different view, right? It's only need to know, only pointed communication. There is no global blockchain at all. Now coming to contracts in Corda. So contracts, as I mentioned, can be written in any JVM language. So Java, Kotlin, there are many others. And it's executed in a sandbox, which is a modified version of a Java virtual machine. And like I mentioned before, there is contract code, and associated with that contract code, you can also associate a legal agreement with it. And the contract code is going to refer to some state information and some participants, right? So each state, the state, think of it as a record that is going to be paired with a contract. So a state cannot be manipulated by multiple contracts. Contract code has to be deterministic, that is needed for any kind of a distributed ledger, but it can reference external information through oracles. So we'll talk about that in the next lecture. So the sandbox, because it's a restricted environment, it guarantees determinism. So that's why that's the modified version of JVM. So it doesn't permit any non-determinism or randomness to get in. Determinism also ensures that the contract code returns the same result across all the peers. So each contract is going to be or transaction is going to be executed independently by multiple peers, but the determinism is ensured because the code will always return the same result. So the contract is only deployed on the peers that are party to an agreement. So the other peers will not even know the existence of this contract. The transaction can have multiple states. So I mentioned the code refers to multiple states. So it can have multiple states that refer to multiple contracts, right? So one transaction can actually operate on multiple contracts, and each contract can have multiple states. For instance, you could, like, here's an example, right? You can have a transaction for swapping a bond for cash. You are selling a bond and you're getting cash in return. So these could be different states that are manipulated by the transaction. So I mentioned about this code is not law, so I won't repeat it again here. So coming to what transactions look like. So transactions reference 0 or more output states and create reference 0 or more input states and create 0 or more output states. This is very similar to Bitcoin, except that state can have arbitrary information. Newly created output states mark the input states as historic. There are three broad types of exchanges or transactions that are specified by Corda. So these are issuances, updates, and exits. So let's just work through an example transaction flow. So there could be an issuance transaction where a new state is created from nothing, right? So you can say, okay, only these entities can create an issuance transactions. There's fine-grained access control. So only maybe a bank can issue, let's say, a financial instrument. So then that issuance is created, and it's recorded on the blockchain. A new state is created. And then the next one may be an update. So the state can go from S0 to S1, and then that will mark the previous S0 as historic. So that is again just basic UTXO. And finally, we could have an exit transaction where an input state is basically expired or matured. Basically, it's a financial instrument that is now no longer valid, so you can exit. So that's also possible. Now transactions can split and merge states. So note that Corda does not have an inherent cryptocurrency, but you can model cash or bonds or other financial instruments as states. So the cash itself can be modeled as a state, and it can map from, let's say, one cash state to another cash state. So cash, it can go from cash 0 to cash 1 in exchange for, let's say, a bond, which goes from bond 1 to bond 2. So these are captured. So this is again a very similar UTXO example. You've split 10 USD into 8 USD and 2 USD, and you're going to consume those in one or more transactions. And this 20 USD can be pointing to a previous transaction altogether. So this is similar split and merge representing fungible assets, very similar to how Bitcoin is a fungible asset. So let's just work through an example of how a transaction and contract execution will work. So let's So let's say this is a transaction between two parties, Alice and Bob, right? Alice first executes the transaction, it calculates the state value, so it calculates state 2 using a flow. So we'll talk about transaction flows in just a little bit. So it's going to execute this logic and it's going to submit a transaction. So that's the first step. So second step, once the contract gets this transaction from Alice, it's going to first verify whether this is a valid transaction. And the state change, it will check whether all conditions or preconditions for this transaction are satisfied. And these preconditions are specified in what is called a flow. So this is, so we'll come to the details of the flow itself, but think that there is a contract, and there are, for each step of the contract, there are preconditions, and the preconditions will specify who needs to sign, perhaps what other information needs to be valid. Maybe it refers to an oracle, an external piece of information. All of that is validated, and only if all the preconditions are met will the contract execution be valid. Right? So that now includes Alice's signature, and that signature is verified. So that's the contract part. The third thing is now Bob might receive this as a peer-to-peer message. So it receives this message from Alice, and then it will check again. It can then execute other validation logic to see whether Bob is okay with signing this this transaction. And this logic can be some external information. So Bob can use information private to just Bob itself and determine whether it wants to sign this. And let's say it agrees to sign it, then Bob will also sign this thing, and the contract can verify that all the conditions are met, and this is actually a valid transaction. Now once this fully goes through, then the transaction is recorded by both Alice and Bob that now this is final. Now coming to the notion of finality. First, there are proposals that are made. So there is a current state and a desired state. So Alice creates this desired state, submits it to, it goes this way this time. So submits it to the contract. But to commit the transaction, it must be signed by all the peers, all the required peers. So Alice proposes, and it's signed by her peer node. So there is signature of Alice that's added to this desired state. And then it's sent to Bob. And then Bob can then figure out whether Bob wants to sign it, and then add Bob's signature. And then finally, once the contract verification validation passes, it's also determined that this state is unique. The input states are not consumed in other concurrent transactions. Once it's determined to be unique, that's through, we'll talk about how that uniqueness is achieved, uniqueness consensus. And then that is recorded as final. So that's once it's recorded and these states are marked historic is when transaction finality is reached. So we still need to see what is this validation that is happening, how is uniqueness achieved, right? We'll go through some of those notions. So the digital signatures are the ones that are giving you immutability and authenticity. So you know that in fact Alice was the one that signed it. No one has modified it since the time Alice signed it. So when an auditor comes and looks at this, they know exactly what has happened. They know that none of these could have been altered, because if they were altered, the signatures won't match, right? So through these digital signatures, you can get immutability and authenticity. But these chain of blocks are only, state information is only available with Alice and Bob. It's not available universally with other nodes. So that's the no blockchain aspect, right? So the state sequences lead to almost like a DAG, right? Each node is going to maintain this DAG of state sequences. Each state could be referring to past state, and it's really a DAG. Okay, so we'll pause at this stage for the first lecture on Corda. So in the next lecture, we're going to look at how the consensus works, how notaries work, oracles as a first-class citizen in Corda. So some of the other aspects. So we've just looked at what a transaction looks like, what the ledger is, the fact that ledgers are distinct states stored by peers and with some overlap. Where the state shared by two peers will be on both ledgers, but there could be state that's in one peer and not in the other peer, right? So it's really a distributed ledger. It's not really a blockchain. So here in our fund reading section, there is links to the Corda interactive white papers. That's just a very high level document, maybe 10 pages or so, I think. The technical white paper is much longer. It's about 60 pages, but it's good information. It tells you, it gives you a good motivating it's motivating article on why they chose to design it this way, why they feel that blockchains as such are not very good for privacy, and you really need this kind of a distributed ledger where transactions are sent to parties on a need-to-know basis, and others will not have even any semblance of these transactions having happened. Okay, so with that, let's move to the next part of Corda. I'll see you soon at the next lecture.